I'm going to start with a remark, as we are all interested in, or at least as this meeting series is devoted to the question of deeper level theory. Our understanding in our search for a deeper level theory is that the Schrödinger equation cannot be the starting point, and therefore, of course, also not the de Broglie-Bohm theory. Rather, we start with an ansatz for a deeper level theory and then derive the Schrödinger equation or the guiding equation, etc. So this is our understanding of what a deeper level theory should be. The outline of the talk is the following. In this sense of deriving a Schrödinger equation, for example, we look at models for trajectories from an ansatz which is generally known as quantum mechanics without wave functions. We heard that about that this morning from Howard Weizmann, and there's other people involved like Poirier, Beckert. And the question is, or what are the possible ontologies related to these ansatzes of QM without wave functions? And our proposal is a sort of quote-unquote cosmological solution. So in our solution, which we generally denote as a two-momentum approach to EmQM, for the guiding law, which I'm going to explain in some detail, and also for dynamical non-locality, as it's called by the Aharonov group, we sometimes use the short term of switching, and I'll explain what we mean by that. And we are going to argue that we can talk about non-local influences which still are no signaling influences. As every theory, we also have some more or less implicit or explicit metaphysical assumption to start with. In this sense, we consider a starting point the Big Bang, or at least the existence of some kind of vacuum energy or dark energy, in that sense that the universe is an energetically open system, which drives not only the expansion, but also each individual particle oscillations. So, as we know, any oscillation can be described in non-equilibrium thermodynamics by a constant throughput of energy to be maintained. And so our answer is that the universe provides just such an energy that the particles are characterized by this frequency omega. And there's, of course, an analogy which is well known. It's related to the experiments by Yves Coudet's group in Paris on the bouncing oil drops on a vibrating bath, where I just want to add that we use this only as an analogy which in several respects doesn't cover the whole model that we will try to develop. But still, it's a good analogy to start with, thinking about this in this direction. And one of the central ingredients which we also use is that there's a resonant interaction of some kind of bouncer with a relevant environment. And I'm going to talk immediately what could be meant by relevant environment. But let's turn back to quantum mechanics without wave functions in the literature. We heard this morning about Wiseman and other model where they show Bohm-type trajectories from many classical worlds approach with certain repulsion effects between the trajectories. For us, we try to develop a different, based on the metaphysical assumption that I just mentioned, our model is one that one could call a superclassical world. That is a classical world with this kind of cosmological non-locality I referred to, which enters the definition of a quantum as the following thing, namely as an emergent system consisting of this bouncer and some wave-like non-local environment which is defined by proper boundary conditions. This means, for example, just in a historical context, that this is not something like the nonlinear wave mechanics of de Broglie, which might superficially be meant by that, because there you also have a highly nonlinear part, and then the wiggling plane wave components. Because in de Broglie's ansatz, he wrote a book about that in the 60s. He considered the quanta as one ontic entity, and we would rather see separate those synchronous elements, the local oscillations and the generally non-local oscillating fields. So here's where the Coudet analogy somehow applies. In our previous work, we derived the Schrödinger equation from a non-equilibrium subquantum dynamics, where the particle is a steady state with a constant throughput of energy. And in particular, we derived the often mentioned osmotic momentum today, independently from the ansatz of Nelson and the expression we have seen today several times, I think. So this brings us to the two-momentum approach to emergent quantum mechanics. A two-momentum would be MV and MU, the forward momentum and the osmotic momentum. And we were able to show that, for example, wave packet evolution can be described classically as ballistic diffusion. The guiding law can be derived from this ansatz and shown to be emergent, but not predetermined. Jan this morning used these terms to differentiate between different approaches. And for us, the most exciting result is that we can show that there's no influence from configuration space necessary in this model, because the guiding equation can be derived in free space. Here's an example of what we did just for one Gaussian slit. We did both analytical calculations and computer simulations. And the analytical situations, velocity fields, acceleration fields, etc., are exactly the results that you obtain also in Bohmian mechanics. And in the simulation scenario, I show here an example of a Gaussian and the Gaussian in a linear potential. We calculate the trajectories, but we also use our ballistic diffusion model to make simple classical simulations, and the trajectories are exactly the same. In the right-hand side picture, you can see that some bright blue spots. These are the trajectories from the simulation, from the calculation, and the black ones are the results from the simulation, so they are really identical. And they are the Bohmian trajectories. It's important to note that we're not talking here about a particle, and then there's some field which you can turn on and off simply, but the particle and the field are permanently, dynamically interlocked. This is something which is very important for the emergent picture that we employ, because it's very often misunderstood in the sense that one doesn't take seriously the effects of the interlocking between the particle and the field at any time, because they usually influence each other at every time step, and we shall see something about that later on. So, one consequence of this is that the velocities or momenta are emergent. So, let's go from one slit to a double slit, where we have predetermined velocities, which means you have a particle plane wave coming in with k and splitting up in Ka and Kb, which also relates to two velocities, Va and Vb. And now we have this interaction, which we indicate like this. So if you introduce the osmotic momentum, which essentially is the gradient of the probability density distributions, then at each time step you have an update of the trajectory, which in the end provides not the predetermined velocities which you see on the top level, which are just straight lines due to momentum conservation, but much more complicated ones. And these are the ones we see, the trajectories that we see in the bottom level, and they are exactly identical to the Bohmian ones, although in our understanding these are average trajectories. So we suppose a more stochastic propagation, and the averaging provides these straight lines, which are then identical with the Bohmian ones. So due to the resonant coupling of the particle with the oscillations of the vacuum, which it's likely to be the zero-point vacuum filling the whole experimental setup, we employ non-local probability density distributions. So, for example, in a typical Gaussian slit, you have this Gaussian, and then you have long wiggly tails throughout the whole apparatus. So this is, so to say, the ansatz which brings non-locality in by hand. But we argue that in order to have a non-local theory, you have to put non-locality in. You don't get non-locality by putting in only local elements. So with this ansatz, we explain the end-slit interference. As I mentioned, we have the forward and the osmotic currents, and the only other quantity that we need in order to describe that are so-called relational intensities, where W now stands for either V or U. It's just a bookkeeping thing. And these relational intensities, so the usual formulation of the de Broglie-Bohm guidance equation, Bohm himself called it indigestible, this influence from configuration space on particle in real space. However, the guidance equation is completely understandable in real coordinate space using, here we go, the relational intensities. And here's the definition. Basically, this is just the intensity at one slit plus all the interferences from the other slits with that particular slit.